Good morning, everybody. My name is René-Paul Lafary. I'm a system engineer for Google. I work mostly in the Google Cloud Platform. And today I'm here to present something pretty exciting. I'm going to show you how you can leverage Tensorflow, a machine learning open source model software to use time series analysis and be able to run all this in the Google Cloud Platform. Why am I talking about this today? Many reasons. First, when you start talking about machine learning, Google is an institution which has been doing a lot of it. We call it like Google Brain internally. We've been doing a lot of machine learning for a lot of different things. You've heard, lately we had this Go championship. We have a lot of things internally, like to do some suggestion of data, advertisement placement, and so on and so forth. And we've been building machine learning models for a long time. What we did with machine learning is decide to open source it. Google in the past had a tendency to write a white paper and let the open source community take ownership of it. Kept a couple of years to build something decent and let others productizing it. We believe that at this point, the machine learning is something important enough that we want to share our knowledge. We want to share what we've been building, and we want to share the TensorFlow as a full open source software that we'll still be contributing to, and that is externalizing some of the things we've been learning in the machine learning world. TensorFlow is open source software library. Some of the magic of TensorFlow is all regarding the distribution of the data and the calculation. So we have data flow graph on the back end, and we have a couple of different models, like from basic regression to some more complex net neural models that are going to be optimized and are going to be able to be intelligently distributed data and so on and so forth to be very efficient. So that's TensorFlow. The second part of the things why Google is relevant in the space is the cloud platform. So the cloud platform is the externalization of our data centers. So Google has been building very big data centers for a long time, for 15 years. We build them from scratch. We build the servers. We build the data centers. We build the whole networking layers to go with it, so software-defined network. And we decided to externalize this through the Google Cloud Platform. So Google Cloud Platform allows you to run simple IaaS, virtual machine if you want to run some of your applications, but we also externalize some of our big data logic. Once again, TensorFlow being one, which is fully open source. We have Dataflow, which is another open source model, which is very good for streaming ingest, and then the whole container world. We believe we have a good amount of stuff there, so we have something called Kubernetes. So you have all those things in open source. You can work with them, and then once you need the scale, just come to Google Cloud Platform. You can run them elsewhere if you want to, but if you come to us, you'll have a big fat network. You'll have very powerful computers at scale. All right, so let's jump right into what we have here. So we have something called Google Cloud Data Lab. So you have the ability, for your data scientists, to easily start up IPython type of environment, which allow you to use some notebooks and do some calculation there. You only pay for when you use them, and you're able just to start those things. The thing I'm going to talk about today is financial time series TensorFlow model. And this is my notebook here. By the way, this is all available for you guys to try. So what I'm going to show you today, if you come home tonight and you want to try it, or maybe tomorrow, you can just go and try it yourself. So what we decided to do in this example is take the data from 8 main exchanges, the closing price of 8 main exchanges over the world, and start to see if we can correlate the closing price, the closing level of those different things, and be able to predict for the last one, which is closing, with the SP 500, and see if there's correlation, and be able to build a model which is going to be able to predict if the other market data can help out with this one. So the first thing we did is we put all of those closing price within our environment. So you can just bring a lot of market data at scale within our environment. And we store there in something we call BigQuery. And you can see right here that very simply, once you put your data within BigQuery, you can query them with SQL-like type of questions, and they're going to come back very quickly. We're able to scale up to petabytes and petabytes of data within BigQuery, and BigQuery is going to be able to return simple SQL requests within seconds. How we do it? Google Magic. We're going to be able to spawn thousands and thousands of instances on the back end and be able to parallelize the workload. Once you have your data, the first thing a data scientist wants to do is be able to actually munch the data, look at the data, play with the data. So Google Cloud Data Lab is integrated with a couple of things. So I mentioned BigQuery and cloud storage, which are some repository where you can put your data for your scientists to work in. But you also have access to Pandas, for example, or Matplotlib if you want to do some calculation with this. So we import in all this data very quickly within some Pandas, and then we're going to be able to merge the data. Okay? So very simple to get the data in the platform and to start playing with them and allowing your data scientists to have access to it. So now we're looking at the data. So you can use regular Pandas type of things to describe the data. You can actually start looking and building some actual graph, and this is running on the back end, and you can see that we look at the evolution of the different markets, and this is the type of graphs that we get. So they're not really linearized, so we want the data to be a little bit more similar in order for us to have an efficient machine learning models. So in order to make it more efficient, you can start using the max closing data to be able to linearize it. So then you can start seeing that the market seems to be correlated. So that's kind of what everybody wants, and everybody knows. However, being able to build a model which is going to be able to represent this correlation is the challenge, and that's where machine learning is going to be helpful. So we are here. We have been able to look at the data, look at the correlation. We can even do some scatter matrix, all those good tools that your data scientists which is able to map every single data against one another. I'll go in more details if you stop by at the booth later, but I just wanted to show you a little bit of the tooling that we can have there. So at the end, we want to normalize the data. The best things to do this is to use the log return, and once we start using the log return here, you can see that we have lot normalized data that we're going to be able to use for our model. The other things we can start looking also at is, are we seeing influence between the data of the same day, the day before, day -2? So you can start having a model which take in account more and more data for you to be able to build the model. Okay. So here we have all our data. We've been merging, we've been playing with it, we've been making it convenient for us to be able to look at the machine learning. So now we can jump into the next things. Tensorflow. So as I said, Tensorflow is open source software, leveraging everything we've been learning in machine learning, and you're going to be able to simply write some multiplication of matrices, some different functions that you might have, some machine learning models in the simplest way, and then we're going to distribute the workload. We're going to shuffle the data. We're going to make sure that the different things are linked, and we're going to be able to run this at scale. You can run it on, in this example, I run it on one machine, but then you have the ability to run it into a distributed amount of machines. So you can say, I have a very complex model. This one is not, but I have a lot of data to go through. I have a very complex model. I want to run it in 1,000 core, for example. And then you can just change one line of code, and it's going to go on the cloud and be able to just being able to do this for you at very big scale. So what do? We first prepare the data to be able to run it. So we create our test data. We're going to be able to get we are 1,400 different data points for each market. We are separating. So in order to do a model and train it, we're going to do 80% of the data will be used to create the model, and 20% is going to be used to validate the model. Okay. So I'm creating the subset, a little bit more of information there. And then I go into how we able to also like know if the data and if our model is pretty accurate. So there's a couple of tools like in machine learning which are pretty easy, but such as like the F1 score and the accuracy. So same thing, there's like very simple way of like calculating those for you to be able like to have like the intelligence of this. Let's jump into our first machine learning model. So simplest of them all, the binary classification, using TensorFlow. So what are like the variables you need to be able like, to build a TensorFlow model? So in order to do models, you need some variables and you need some operations. An operation that then is going to be like being able to be distributed. So here we can see that we create a couple of things. So our feature data is the data we're going to use in order to train the model. And that's going to be like the other actual classes, which are like the results of the things. And then we create weight and biases. Weight and biases are going to be used to create the model. And the way we're going to do this is just, when you look at like a binary classification, it's pretty straightforward. We're just going to do a multiplication of matrix between the feature data and the weight plus the biases, and then we're going to do a softmax regression. Softmax regression is a pretty common way of wrapping up any type of regression and machine learning models, which are going to just look at the optimization of the model. The model is then going to be iterated against a cost. So how do you know if your model is good or not? You minimize the cost. The cost is the divergence between what is your real data and what has been projected to be. So you do the comparison, and the more the cost goes down, the better you are. So the training step will be just to train this and minimize the cost. So that's how we create the thing. Our model is being created. So we have our model, we have the cost, we have the training step. Let's go for it. So now we're going to iterate against this model 30,000 times using every single data set. So 80% of our data set, and we're going to iterate, and then we're going to see against the 20% left if it's accurate or not. So in order to do this, like I have a pretty powerful machine on the back end, and I'm able, like right now, like you can see it's running, and that's the simpler model, so it should be taking a little bit of time, but not too long. Start imaging, so after 5,000 iteration, we're like 66% accuracy. So that's not too bad with this type of data. Don't forget that like when you start like building a machine learning model, what's important is the quality of the data and a good amount of data. You don't need to have too much data, but like this model is pretty simplistic. So we can see that at each iteration, the model is getting better and better. And we reach at the end like 67% of accuracy, which is not too bad for the simplistic binary classification that you can have. Okay, great, simple. You get the data, you play a little bit with it, you can build a machine learning model super easily. Let's go to the next level. Okay, now I want something a little bit more complex, and it's still going to be easy. So what we're going to do here is we're going to like try to do a feed-forward neural net with 2 hidden layers. Okay, so that's another model that like we use a good amount at Google, and that's something that you can do. So how you do this? Instead of like 1 layer of weights, you do like 3 layers of one. 2 are going to be for the hidden layers. They have like a big weight, so like a 50-node type of thing. So it's pretty big. The second layer is like 25, and then the last one will be like the aggregation through a softmax again. You just have to do those 3 simple line of code. Hidden layer using this layer of weight, another one with this weights, and then the softmax. The cost is the same, the logic is the same. Okay? Here we go again, and then we're going to run it against the same thing. So right now, I'm going to be a little bit limited by this machine. So you can see it's like a little slower than the others, because we're actually doing a lot of things. We're going through this data, but like 2 hidden layers and a lot of distribution in the back end. So it's a little slower, but you're going to see that like the model and the precision of the model is going to be a little higher. If I wanted to, I could have like been able like to show this in the cloud, and that would be a lot faster for you to be able to run it. Demo effect. It does take a little time. There you go, 76%. And I can tell you that like with this data set, I don't think you can get like much much higher than this. And we have been able to, in less than 15 minutes, in 14 minutes and 50 seconds, we ingest the data, we noodled it, we use a couple of models in it, and we've been able to do this easily in the Google Cloud environment. That's it for me.